go ahead and get started. I don't think it's going to be super long today. I don't have a ton, but I am talking about missing data. And missing data are just part of our world. When we were in stats class in school, the textbook problems worked out perfectly. But in the real world, it's not quite so beautiful. So even in well-designed and controlled studies, missing data are going to occur in almost all research. And missing data can reduce the statistical power of a study. It can produce biased estimates, which lead to invalid conclusions. So there are a lot of ways to handle missing data. But before we jump into the various techniques, we need to identify what missing data are and define. So the first question we have is, what is missing data? And why do we care about it? So missing data is defined as a data value that is not stored for a variable in the observation of interest. This can cause problems, like I said, with reducing statistical power. It can bias your estimation of parameters, can reduce the representativeness of the samples, and it may significantly complicate the analysis of the study. Now, missing data can occur due to a myriad of reasons. So it might be corrupt data. It might be failure by extracting data from your source. And maybe participants are not feeling comfortable responding to certain questions. Or, like I said, there are a myriad of other reasons. This can cause absence of the data, which is what we term missing data. In other words, the missing data and the data value is not stored. All right, so there's three real types of missing data. The first are missing completely at random. In missing completely at random, the probability of data being missing is the same for all observations. So in this case, there's no relationship between the missing data and any other values being observed or that are unobserved for data which are not recorded within the given data set. There's no pattern, so the missing data are completely independent of all other data. While this is ideal, it is quite unlikely. If data are missing, it could be due to human error, some system or equipment failure, loss of sample, some unsatisfactory technicalities while recording values. It's definitely not possible to predict values with the rest of the variable data in data that are missing completely at random. So, for example, during data collection, if you have a particular sample that gets lost due to carelessness, this is an ideal case for missing data because statistically the analysis will not be biased. But you shouldn't assume the presence of missing completely at random because it is a very rare situation. So the next two types of missing get a little more problematic and then are the most problematic, which is missing at random. So missing at random means the probability the responses are missing depends on the set of observed responses, but it's not related to the specific missing value which we're expecting to obtain. This is more realistic, and what I mean by all of that is the reason for missing values can be explained by variables which we do have complete information because there is some relationship between the missing data and the other values. In this case, the data aren't missing for all of the observations. It's missing only within some subsamples of the data. So there is some pattern in that missing data. So, for example, let's consider a survey about time spent on the internet, which has a section about time spent on platforms like Netflix, Amazon Prime, etc. It may be observed that older people over the age of 45 are less likely to fill in that question than those who are younger. This is an example of missing at random. Here, the age parameter decides if the data will be missing or not. And missing at random occurs very commonly and much more so than missing completely at random. And then our third type of missing data are missing not at random. So missing not at random values depend on the unobserved data. So there is some structure and pattern of missing data, and other observed data cannot explain it. So at that point, it's considered to be missing not at random. This is very problematic because the only way to obtain an unbiased estimate of the parameter is to model the missing data. And the model may be incorporated into more complex one for estimating the missing value. So a couple of ways to prevent missing data as much as possible. The best possible method of handling it, of course, is prevention. So first, the study design should limit the collection of data to only those data that are necessary. So minimize the number of follow-up visits, collect only essential information at each visit, and develop user-friendly case report forms. Make it as easy as possible to collect the data so that you can collect a full data set. Second, before the beginning of the clinical research, a detailed documentation of the study should be developed in the form of a manual of operations. This is going to include the methods to screen participants, the protocol to train the investigators and participants, methods to communicate between investigators or between investigators and participants, implementation of the treatment, procedure to collect, enter, and edit the data. So it's a very detailed plan, which is going to pair well with the third preventative measure, which is before the start of the study, a training should be conducted to instruct all personnel related to the study on all aspects of the study. So you want to train on participant enrollment, collection of data, and entry of data, and implementation of any kind of intervention if it is an interventional study. The fourth measure is if you have a small pilot study that's performed before the start of your main study, then it may help to identify the unexpected problems which are likely to occur during the study. That will help you to reevaluate questions and hopefully reduce the amount of missing data in your main study. Fifth, the study management team should set a priority targets for the unacceptable level of missing data. So with these targets in mind, as you're collecting data, especially if it's a multi-site data, this is where queries come in. You're going to monitor and report in as close to real time as possible any missing data that you see and try to get that taken care of. Sixth is study investigators should identify and aggressively, though not coercively, engage the participants who are at the greatest risk of being lost during follow-up. Finally, if you have a prospective study and you have patients that decide to withdraw, so you know that you're going to have missing data from that point forward, and you want to make sure that the reasons for withdrawal are recorded for subsequent analysis and interpretation of the results so that you know that those data aren't just missing at random, but they're missing because the patient or subject discontinued the study. All right, so you may know the Titanic data set. I'm going to use this just for a little bit of demonstration. The Titanic data set is used a lot in machine learning as an example data set. It includes information from individual passengers on the Titanic, and it does not include information from the crew, but it does contain actual ages, names, locations, fares, a good bit of information from those individuals who are on the Titanic. And it provides a nice data set for examining survival if you're working on learning survival analysis. It provides a nice data set for missing data because some of the data are missing. And so it's a fairly well-known data set. The principal source for the data is the Encyclopedia Titanica. The data set itself was begun by a variety of researchers, and there's reference for one of the original sources. All right, So the first thing that I wanted to show you, I threw this data set into REDCap. And if you have not utilized the missing data feature in Stats and Charts, it is so easy to help you identify missing data and to populate those data. So I have a quick little screen grab. We are in the Exports, Reports, and Stats section for the Titanic database. So here I'm going to go to Stats and Charts and scroll down. You can see that the first few were completed fully. Then we get to age, and age has 177 missing variables. So if you click that link, it opens them up, and I can see all of the ones missing. I click on a number, and in a separate window, it's going to open it up to the field that is missing so that I can populate that field. Once I'm done populating that field, I'm going to save an exit form. I can close out of that window, and my report is going to, my report is going to be there so I can click on the next number. That's a fast and easy way to populate missing data if those data just were overlooked during data entry. If those data were not overlooked during data entry and you actually have missing data, we then have to utilize techniques for handling those data. So the first thing that we want to do is to use a data analysis method, which is robust to the problems caused by missing data. An analysis method is considered robust to missing data when there is confidence that mild to moderate violations of the assumptions will produce little to no bias or distortion in the conclusions drawn on the population. However, it's not always possible to use those techniques. Therefore, there are a number of alternative ways of handling missing data. So we're going to walk through some of these, and we'll kind of open it up for discussion. So you're going to want to analyze each column with missing data carefully to understand the reason behind the missingness of those values, as this information is critical to choosing the strategy for handling the missing values, because some of the methods are going to be more appropriate for different types of missing data. There are two primary ways of handling missing values. One is deleting the missing values, and two is imputing the missing values. So generally speaking, simply deleting the missing values is not recommended until you understand the type of missing value. It is a quick and dirty technique that you can use, and it is frequently used. But if the missing value is the type of missing not at random, then it absolutely should not be deleted. And if the missing value is the type missing at random or missing completely at random, then it can be deleted. In the analysis, all cases with available data are utilized, while missing observations are assumed to be completely missing at random and addressed through pairwise deletion. The disadvantage of this, of course, is that you might end up deleting some useful information from the data set. And there are other ways that you can use to impute, which will retain your remaining data that were there. So first, let's look at listwise or casewise deletion. This is simply omitting those cases with the missing data and analyzing the remaining data. By far, this is the most common approach to missing data, and the approach is most frequently used when you're trying to handle missing data. I'm looking at the data set example I put here, and it is complete, so I'm not sure why I put that there. Apologies for that. Some researchers do insist that listwise or case deletion will introduce bias in the estimation of the parameters, but if the assumptions of missing completely at random are satisfied, listwise deletion is known to produce unbiased estimates and conservative results. When the data do not fulfill the assumption of missing completely at random, it may cause bias in the estimates. If there's a large enough sample where power is not an issue and the assumption of missing completely at random is satisfied, the listwise deletion may be a reasonable strategy. However, if it's not a large sample, then the listwise deletion is not an optimal strategy. So when we look at listwise deletion, and I put this Titanic data set up here. This is not the screen grab that I thought I was going to have, but There are over 860 cases in that data set. If you look at Cabin, I believe, it's not very populated. So if you complete list-wise deletion on Cabin, it is, so it's the NAN is absent, missing data. If you complete a list-wise deletion on these data, and you're including for Cabin, it reduces your data set from 860 something to 87, which can be exceptionally problematic because not only have you just significantly reduced your sample size, but you've probably gotten rid of a lot of observations that are very different than the remaining sample. And so you're going to skew or bias your results. All right, the next method or technique is pairwise deletion. So pairwise deletion eliminates information only when the particular data point needed to test a particular assumption is missing. So if there are missing data elsewhere in the data set, the existing values are used in the statistical test. So in the example earlier, if you were not including Cabin, then significantly more, depending on which variables, on the measure of all of the records would be retained. Since pairwise deletion uses all of the information observed, it preserves more of the information than the listwise deletion, which may delete the case with any missing data. This approach presents the following problems, though. The parameters of the model are stand on different sets of data with different statistics. So you're going to have different populations, sample sizes for the different analyses that you run. And it can produce an intercorrelation matrix that's not positive definite, which is likely to prevent further analysis. Pairwise deletion is known to be less biased for missing completely at random or missing at random data, and the appropriate mechanisms are included as covariates. However, if there are many missing observations, the analysis is still going to be deficient. So if we don't delete the data, then we can look at some imputation methods. So in the first one, you're going to look at mean or mode or median, depending on your data type, imputation or substitution. In mean substitution, the mean value of a variable is used in place of the missing data value for that same variable. This allows the researchers to utilize the collected data in an incomplete data set. The theoretical background of the mean substitution is that the mean is a reasonable estimate for a randomly selected observation from a normal distribution. However, with missing values that are not strictly random, especially in the presence of great inequality of the number of missing values for the different variables, the mean substitution method may lead to inconsistent bias. Also, this approach adds no new information, but only increases the sample size, which leads to an underestimate of the errors. So mean substitution is not always accepted. Also, like I said before, the type of substitution depends on the data. With mean substitution, you are going to use that if you have ratio level data. If you have outliers, then it's not going to be appropriate. So that scatter plot that I showed earlier when we were looking at replacing or identifying mean data can also be used to identify outliers. You can click on that outlier and it'll have the same functionality as clicking on the missing. It's going to take you to that value in the record. You can evaluate whether that's an accurate value or an error. In such cases, you have to treat the outliers like that. If the outliers are real, then it's probably going to be better to use the median value for imputation because that's the middlemost value. And so it is not affected by the skew of outliers. And then mode is going to be the most frequently occurring value. And so you're definitely going to want to use that in the case of categorical features if you so choose to use a substitution technique. All right, the next technique is regression imputation. So imputation is the process of replacing the missing data with estimated values. Instead of deleting any case that has any missing value, this approach preserves all cases by replacing the missing data with a probable value estimated by other available information. After all missing values have been replaced by this approach, the data set are analyzed using the standard techniques for a complete data set. In a regression imputation, the existing variables are used to make a prediction, and then the predicted variable is substituted as if it were an actually obtained value. This approach has a number of advantages because the imputation retains a great deal of data over the listwise or pairwise deletion and avoids significantly altering the standard deviation or the shape of the distribution. However, as in mean substitution, while regression imputation substitutes a value that's predicted from other values, no novel information is added. So simply the sample size is increased and standard error is reduced. If you have repeated measures, then last observational carried forward may be an appropriate approach. So in this method, which is one widely used method for repeated longitudinal time series approaches, the last observation is carried forward for a single subject. So when a subject has a missing value, then the one from the previous observation is carried forward. This method is advantageous as it's easy to understand and communicate between statisticians or clinicians, but it strongly assumes that the value of the outcome remains unchanged by the missing data, which seems unlikely in many settings, especially if you are introducing or utilizing an intervention where you do expect to see change. It does produce a biased estimate of the treatment effect and underestimates the variability of the estimated result. Accordingly, the National Academy of Science has recommended against the uncritical use of the simple imputation, including last observation carried forward and the baseline observation carried forward, stating that single imputation methods like last observation carried forward and baseline observation carried forward should not be used as the primary approach to the treatment of missing data unless the assumptions that underlie them are scientifically justified. All right, our next technique is maximum likelihood. There are a number of strategies using the maximum likelihood method to handle missing data. In these, the assumption that the observed data are a sample drawn from a multivariate normal distribution is relatively easy to understand. After the parameters are estimated using the available data, the missing data are estimated based on the parameters which have just been estimated. When there are missing but relatively complete data, the statistics explaining the relationships among the variables may be computed using the maximum likelihood method. That is, the missing data may be estimated using the conditional distribution of the other variables. Next up is the expectation maximization. This is a type of maximum likelihood method that can be used to create a new data set, in which all missing values are imputed with values estimated by the maximum likelihood methods. This approach begins with the expectation step, during which parameters, such as variances, covariances, and means, are estimated, perhaps using listwise deletion. Those estimates are then used to create a regression equation to predict the missing data. The maximization step uses those equations to fill in the missing data. The expectation step is then repeated with the new parameters, where the new regression equations are determined to fill in the missing data. The expectation and maximization steps are repeated until the system stabilizes, when the covariance matrix for the subsequent iteration is virtually the same as that for the preceding iteration. An important characteristic of the expectation maximization input is that when the new data set with no missing values is generated, a random disturbance term for each imputed value is incorporated in order to reflect the uncertainty associated with the imputation. However, the expectation maximization imputation has some disadvantages. This approach can take a long time to converge, especially when there's a large fraction of missing data, and it's too complex to be acceptable by some exceptional statisticians. This approach can lead to the biased parameter estimates and can underestimate the standard error. For the expectation maximization input method, a predicted value based on the values that are available for each case is substituted for the missing data. Because a single imputation omits the possible differences among the multiple imputations, a single imputation will tend to underestimate the standard errors and thus overestimate the level of precision. Thus, a single imputation gives researchers more apparent power than the data in reality. Okay, one more. Multiple imputation. Multiple imputation is another useful strategy for handling missing data. In a multiple imputation, instead of substituting a single value for each missing data, the missing values are replaced with a set of plausible values which contain the natural variability and uncertainty of the right values. This approach begins with the prediction of the missing data using the existing data from the other variables. The missing values are then replaced with the predicted values, and a full data set called the imputed data set is created. This process iterates the repeatability and makes multiple imputed data sets, hence the term multiple imputation. Each multiple imputed data set produced is then analyzed using the standard statistical analysis procedures for complete data and gives multiple analysis results. Subsequently, by combining these analyses, a single overall analysis result is produced. The benefit of multiple imputation is that in addition to restoring the natural variability of the missing values, it incorporates the uncertainty due to the missing data, which results in a valid statistical inference. Restoring the natural variability of the missing data can be achieved by replacing the missing data with the imputed values, which are predicted using the value, variables correlated with the missing data. Incorporating uncertainty is made by producing different versions of the missing data and observing the variability between the imputed data sets. Multiple imputation has been shown to produce valid statistical inferences that reflect the uncertainty associated with the estimation of missing data. Multiple imputation turns out to be robust to the violation of normal assumptions and produces appropriate results even in the presence of a small sample size or a high number of missing data. With the development of novel statistical software, this approach may be utilized easily, though it is somewhat complex and can take a considerable amount of time in certain circumstances. The last approach that I'm just going to touch base is sensitivity analysis. This is defined as the study which defines how the uncertainty in the output of a model can be allocated to the different sources of uncertainty in its inputs. When analyzing the missing data, additional assumptions on the reasons for the missing data are made. These assumptions are often applicable to the primary analysis. However, the assumptions cannot be definitively validated for the correctness. I will reference back to Suma's presentation last month when she spent the entire Lunch and Learn educating us on sensitivity analysis. All right, so in conclusion, missing data reduces the power of a trial. Some amount of missing data is expected, and the target sample size is increased to allow for it. However, more attention should be paid to the missing data in the design and performance of the studies and in the analysis of the resulting data. The best solution to the missing data is to maximize the data collection when the study protocol is designed and the data are collected. Application of the sophisticated statistical analyses should only be performed after the maximal efforts have been employed to reduce missing data in the design and employed appropriate prevention techniques has been used. A statistically valid analysis, which has an appropriate mechanism for assumptions for the missing data, should be conducted. Single imputation and last observation carried forward are not optimal approaches for the final analysis, as they can cause bias and lead to invalid conclusions. All variables which present the potential mechanisms to explain the missing data must be included, even when these variables are not included in the analysis. Researchers should seek to understand the reasons for the missing data. Distinguishing what should and should not be imputed is usually not possible using a single code for every type of missing value. It's difficult to know whether the multiple imputation or full maximum likelihood estimation is best, but both are superior to the traditional approaches. Both techniques are best used with large sample sizes. In general, multiple imputation is a good approach when analyzing data sets with missing data. And that is all I have. I did utilize this article a lot, so I reference it at the bottom. I'm going to open it up for thoughts, comments, questions, discussion.